I am Dr. Nisha Shantakumari, Department of Physics at Salim College, Vellore. I would like to present a short lecture on Introduction to Quantum Mechanics. Let me state the inadequacy of classical mechanics. We know that classical mechanics is based on Newton's three laws: law of inertia, law of force, and law of action and reaction. Classical mechanics could explain correctly the motion of celestial bodies like planets, Earth, stars, etc. And also, it could explain the motion of microscopic bodies moving with non relativistic speed. But it could not account for certain factors, like it could not explain the non relativistic motion of atoms, electrons, protons, etc. It could not account for the stability of atoms. It could not explain the observed spectra of black bodies, and it could not explain the origin of discrete spectra of atoms. So, new concepts were developed. These concepts led to the discovery of quantum mechanics. The quantum mechanics was developed in two stages. The first stage began with Max Planck's theory that radiation is emitted or absorbed by matter in the form of discrete packets called quanta of energy h nu, where h is called Planck's constant, nu is the frequency. Then the second stage developed with matrix mechanics introduced by Heisenberg in the year 1925 and with wave mechanics developed by Schrödinger in the year 1926. In this mechanics, classical mechanics ideas were developed with Louis de Broglie's theory, which states that, like radiation, matter, which is made up of particles, possess dual nature. That is, even though matter is made up of particles, these particles behave like waves under certain conditions. The waves associated with material particles are called matter waves, and the wavelength of the matter waves is given by lambda is equal to h by p, where h is Planck's constant and p is the momentum. So, according to Louis de Broglie's theory, to every moving particle we can associate a wave. The wave associated with the particle in motion is represented by a complex variable quantity called wave function, and it is denoted as psi. The wave associated with the particle in motion is represented by a complex variable quantity called wave function, and it is denoted as psi, which is a function of r comma t. It is a complex quantity, so the complex conjugate of psi is denoted as psi star. The probability of finding a particle in unit volume is called probability density, and it is denoted as P of r comma t. The probability density P of r comma t is equal to psi star, or it is equal to modulus psi square. The total probability of finding a particle in a region is unity. Now let us see the physical significance of the wave function psi. Psi is finite for all values of x, y, and z. Psi is single valued psi, and its partial derivatives dou psi by dou x, dou psi by dou y, and dou psi by dou z are continuous for all the values of x, y, and z. Psi vanishes at infinity. That is, psi is equal to 0 as r tends to infinity. It also vanishes at boundaries. These are the physical significances of the wave function psi. I stop here. My next lecture will be on postulates of quantum mechanics. Thank you.